Okay, class. So this is a video on Unit 9 on random variables. Under the lesson, let me get rid of this. Under the lesson, discrete random variable, right? And this is the video for the exercise of probability with discrete random variable. So, right, before we go to discrete random variable, I need to kind of explain what discrete means. So, discrete random variables are variables that are taking on values that you can actually count, like the numbers on a die, you can count, right? Um, like colors, how many colors there are, you can count those. So, opposite of discrete random variables are continuous random variable, which we will talk about it after this particular lesson. And this and continuous are random variables that are variables that kind of you can't really count them, but you can measure things like height, right? Height, you cannot really have a precise height every single time. And it varies from one person to another, so much so that it's actually, it's really hard to have so many different um, discrete values for height because they're just so varied. And so that's why it's placed under continuous. So discrete random variable. So for example, if you look at this, the first digits of data entries in most real world data sets are not uniformly distributed, right? So they're not uniform, right, in most real world data. The most common first digit is 1, followed by 2, and so on, with 9 being the least common first digit. This phenomena is known as Benford's law. I don't know about such a law, but there we go. The table below is the probability distribution for Bamford's law, where the random variable d, in this case, it's discrete random variable because all the values that you see right here, they are countable, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And they each have its corresponding probability. So for the digit one to happen, it's zero point 0.3. It's about 30% of the time. So this is the distribution model, right? It's given to you for D. They ask you what is the probability that a randomly selected data entry has a first digit greater than 7. So greater than 7. So let me ask you, if it's greater than 7, does it include 7? And the answer is no, right? When it says greater than 7, 7 is not included. So if they are trying to find the probability of first digit greater than 7, all you all you have to look at is for the digit 8 and the digit 9, and you got to add those two together. So 0.051 plus 0.046. Um, Actually, if there's a way to actually do this and put my calculator up, that will be kind of helpful. Let's see. And yep. And I don't want me to clear this. All right. And I need to reduce this. There we go. I actually don't want, okay, view. I don't want hide the key. All right. And expand this as big as we possibly can. And that's not okay. So hopefully this will be it. There you go. So what I need to do is take 0.051, sorry, 0.051, add it to 0.046. That will give me the probability of the first digit greater than 7. And here the answer is 0.097. Okay, so hopefully that makes sense, right? So let's look at another question. The American Community Survey is completed by the U.S. Census Bureau to obtain information about households in the US. One variable of interest is how many people reside in each household. Vacant households were recorded as having 0 people based on data from 2014. Here is the partially completed probability distribution of H, right? Where the number of H represents the number of people residing in a randomly selected US household. So zero, what's the probability of zero? So there's a household 1, 2, 3, 4, and 5 plus. That means 5 and above. And this is an incomplete, partially completed probability distribution. So to find this, a valid one is one that this all will add up to 1. So in order to find this, all we have to do is take 1, subtract away, what is this? 0.24, right? Subtract away, what is the next one? For h equals to 2, 0.3, subtract 0.14, subtract 0.11, subtract 0.09, and that should give me 0.12. So here, probability of 0 people residing, right? So having vacant households that were recorded as having 0 people is 0.12. Okay, so let's continue. So Hugo plans to buy uh, packs of baseball cards until he gets the card of his favorite player, but he only has enough money to buy at most 4 packs. So suppose that each pack has a probability of zero point 0.2 of containing the card Hugo is hoping for. Let the random variable x be the number of packs of cards Hugo buys. Here is the probability distribution for x. So 1, 2, 3, 4, voila, is a discrete random variable because we can count the number of packs. And that's a valid that's a valid probability distribution because this all add up to 1. So they ask, find the indicated probability such that x is greater than equals to 2. So does it include 2? Yes, it does. So we add 0.16 plus 0.128 plus 0.512. That will give us 0.8. Sweet. So hopefully that will help answer some of your questions. You want me to do one more? I'll do one more. So Cora is playing a game that involves flipping 3 coins at once. Let the random variable h be the number of coins that land showing heads. Here is the probability distribution for h. So h is a discrete random variable because you can count the number of heads. So 0, 1, 2, and 3, and those are the corresponding probability. What is the probability that Cora flips no more than 1 head? No more than 1. Does it include 1? Yes. So no more. So it's not 2, not 3, but no more than 1. Can it be less than 1? Yes, it can. So it's this 0.125 plus point right here 0.375. It's 0.5. All right. So if you have any questions, please let me know. If not, thank you.